Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate Programs, Postgraduate Certificate, Certificate in Energy Technology and Management, CETM, OEY-01 Energy Resources and Conversion Processes, Block-1 Conventional Energy Sources, Unit-1 Introduction to Energy and its Various Forms. 1.1 Introduction. We use energy every day. Energy is very fascinating. It surrounds us in different forms such as heat, light, and electricity. When you are reading these lines, you are using energy which you have consumed either in your breakfast or lunch, dinner. Any living organism relies on an external source of energy, e.g., radiation from the sun in the case of green plants, chemical energy in some form. In the case of animals, to be able to grow and reproduce. Energy is always conserved, which means that it can neither be created nor be destroyed. Energy may be transformed from one form to another. There is no absolute measure of energy, because energy is defined as the work that one system does, or can do, on another. Thus, only the transition of a system from one state into another can be defined and thus measured. What is energy, its various forms and the energy contents of different energy sources all will be discussed in this unit so that you could understand subsequent units easily. Objectives. After going through this unit, you will be able to explain the meaning of energy and its unit, understand various forms of energy, describe the conventional energy sources, know the world reserve of energy, and define the calorific values of energy sources. 1.2 Energy. Energy is all around us, exists in many forms and can be detected by our senses and instruments. Energy is stored in many different situations, can change form, and can be used to do useful work. In other words, we can say that it is difficult to define energy, but it is easy to understand what energy can do. You must have seen the power failure in your village, house. You must have noticed various things which have stopped working at that point of time. The fans, bulbs, tube light, TV, electric washing machine, electric toaster, electric motor etc. all have stopped working because these appliances work only when electricity passes through them. Thus we can see that electricity can make things move, it produces light, it heats water, and that is why you say that electricity has energy. You do many work, you move, you read, you play, and for all these activities, you need energy which comes from the food you consume. You may conclude that food has energy. In a similar way, you can observe several things around you which are changing. All changes in the universe involve the interactions between energy and matter. Solar energy is the original source of most of the Earth's available energy. Matter can be converted into energy. The total amount of energy in a closed system is conserved, although it is not always available to do useful work. 1.2.1 Energy defined. We will now say that anything that can assure a change has energy. Energy is widely defined as the capacity, ability to do work. You can say that work is the transfer of energy from one form to another. Whether all energy is transferred to work or not, it depends upon the quality or grade of the energy. The two most common forms of energy used by us are heat and electricity. Energy is defined. Energy might be best described when we see what it can do for us. You know that we can't see energy, but we can feel its effects. We cannot make energy, but we can definitely use it. We can't destroy energy, but we can waste it, which means that we use it inefficiently. Energy is defined as the ability or the capacity to do work. We use energy to do work and make all movements. When we eat, our bodies transform the food into energy to do work. When we run or walk or do some work, we burn energy in our bodies. Cars, planes, and machinery also transform energy into work. Work means moving or lifting something, warming or lighting something. There are many sources of energy that help to run the various machines. Running water and wind can move turbines due to kinetic energy. 1.2.2 Energy measurement. One of the basic measuring blocks for energy is called a BTU, a British thermal unit. BTU is defined as the amount of heat energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at sea level. 1 BTU equals about 1 black tip kitchen match. It takes about 2000 BTU to make a cup of coffee. Energy can also be measured in joules. 1 joule is the amount of energy needed to lift 1 pound to about 9 inches. It takes 1000 joules to equal a BTU. It would take 2 million joules to make a cup of coffee. Joule is named after an English physicist named James Prescott Joule who discovered that heat is a type of energy. Around the world, scientists measure energy in joules rather than BTU. It is much like people around the world using the metric system, meters and kilograms. Like in the metric system, you can have kilojoules. Kilo means 1000, therefore, 1000 joules equals 1 kilojoule equals 1 BTU. Power is the rate of doing work. It is defined as follows. Power equals work, time equals height x weight, time. 1.2.3 Energy source. An energy source is a substance or a system that is capable of delivering net kilowatt hours of energy to the system. Gasoline is a net energy source. The various energy sources are renewable energies like biomass, biofuels, biogas, wind, hydropower and commercial energy, non-renewable or conventional sources like coal, oil and gas. 1.2.4 Energy carrier. Energy carriers move energy in a usable form from one place to another. Batteries, flywheels, utility pump storage and terrestrial hydrogen are typical examples. They are energy carriers, or you may call them energy transfer systems, because you first have to fill them with energy before you can empty them. All energy carriers consume significantly more existing old energy than they can return as new. An energy carrier is inherently a pollution amplifier that will magnify the pollution created by its underlying sources. 1.2.5 Energy sink. An energy sink is any means that consumes more old energy than it returns as new energy. Solar photovoltaic PV systems may be a net energy sink because PV has in totality consumed far more old energy than it has yet to deliver as new. If your solar panel is generating Rs 10 worth of electricity a day and the interest cost is Rs 12 a day, you have a net energy sink. 1.3 Grades of energy. Let us consider an example shown in figure 1.1 where we have shown two forms of energy, electricity and thermal, being converted into work. The electricity or electrical energy is capable of almost complete conversion into work, while thermal energy is capable only of partial conversion into work. You can say that the electricity is of high quality or high grade of energy. Also, the same quantity of energy after use has less capacity for work. In other words, you can say that it is the ability of energy to do work which sets its quality. Examples of quality of energy. 1 kilojoule of electrical energy has more capacity for doing work than 1 kJ of wood energy. 2 1 kilojoule of wood energy has more capacity for doing work than 1 kilojoule of internal energy of seawater. Figure 1.1. Energy conversion into work. Look at the screen. 1.3.1 High-grade energy. When energy is concentrated in a small space, we call it a high-grade energy like electricity and chemical energy. The high-grade energy should be used for high-grade applications rather than low-grade applications like heating of water. The particles or molecules that store these forms of energy are highly ordered and compact. 1.3.2 Low-grade energy. Low-grade energy is characterized where the particles or molecules that store this form of energy are randomly distributed. For example, heat is low-grade energy. 1.3.3 Energy use. You are aware that energy is required for doing any kind of work. Energy lights our cities, powers our vehicles, and runs all kinds of machinery in industries. It provides thermal comfort in our homes, cooks our food, plays our music, and gives us pictures on television. You can't imagine present-day life without energy. Energy is derived from various sources. The use of an energy source depends upon the amount of energy available, ease of distribution, the extent to which energy can be concentrated, and the convenience with which it can be used. We are responsible for the conservation, intelligent and safe use of energy. 1.4 Basics of electrical energy. The flow of electrons is characterized as electricity. The electric current is of two types: direct current, DC, and alternating current, AC. The main characteristics of DC and AC are given in Table 1.1. Table 1.1. Characteristics of DC and AC. Look at the screen. 1.4.1 Current, I, and voltage, V. The rate of flow of charges is called current, I, and is measured in ampere, A. The electric potential is measured in volt, V. Imagine a resistance of 1 ohm. When a current of 1 ampere flows through this resistance, R, a potential of 1 volt appears. The convenient unit of voltage is kilovolt, kV, which is equivalent to 1000 V. The relationship between current, I, and voltage, V, is established by famous Ohm's law. Mathematically, it is expressed as follows. V equals IR. 1.1. Where R is the resistance, measured in ohm, omega. This is a linear relation. If you double the voltage, V, then for the same value of R, you get twice the current. Alternatively, if you double the voltage and want to keep the current the same, you must double the resistance. 1.4.2 Electric power. Our electricity bill essentially measures the amount of current that we use, but we use this current as power. Since V equals R, I, then power, P equals IV equals I, R, I, equals I2, square R. 1.2. You cannot change the resistance of the toaster element in your daily use, but you must have enough power radiated by the toaster to serve your purpose. Usually, the resistance of the element is quite high and therefore it resists the movement of the electrons and the element heats up. The more current you allow, more is the power that is radiated by the element as heat. You pay for I, but it is I2 that determines the power usage, and hence you end up paying for it. The longer you use the toaster, the more energy you use. Heat dissipation is energy lost by the toaster, and this loss is unavoidable. Now you can go ahead to see the efficiency of electricity use in toaster. If R equals 1, power dissipated as heat equals 20.6 W. This means that in order to deliver 1000 W that you need, you have to generate 1020.6 W. The overall efficiency is 101020.6 equals 0.97 equals 97%, for which you have to pay. Higher is the power required, higher is the heat dissipated, and hence lowers the overall efficiency. That is why higher voltage is needed to transmit power from power stations to the end user. This is done by using transformers. Point to remember. A transformer uses current in one coil to induce current in another. The induced voltage is given by Vout equals Vin, N2, N1, where N1 equals number of coils in the primary, N2 equals number of coils in the secondary. When N2 is less than N1, we reduce Vout. Energy conservation tells us that Vout, I out equals Vin, I in. 1.3. You may observe the following. Vin is very high, In is low for reducing transmission losses. Remember I2R. When Vin is stepped down to produce Vout, this voltage we get in our homes, I ought, increases to run our appliances. You are familiar with active power, kW, and kilowatt hour, kWh, but less familiar with kilowatt ampere, kVA, and reactive power, kVA. Let us introduce all these powers in order to facilitate you to learn energy conservation easily at a later stage. 1.4.3 kilowatt, kW, active power. kW is called active power, also called as working power, actual power, and real power. It is the work-producing part of apparent power. For a single-phase and three-phase electric circuits, it is given as follows. For a single phase, kW equals voltage into amperes into power factor upon 1000, 1.4. For a three-phase, kW equals 1.732 into voltage into amperes into power factor upon 1000, 1.5. 1.4.4 kilovolt ampere, kVA. It is called the apparent power and is a measure of electric load on a circuit. For a single phase and three-phase circuits, it is given as follows. For a single phase, kVA equals voltage into amperes upon 1000, 0.1.6. For a three-phase, kVA equals 1.732 into voltage into amperes upon 1000, 0.1.7. 1.4.5 reactive power, kVA. kVA is the reactive power and is that portion of apparent power which does no work. This is needed in all types of magnetic equipments like motors, transformers etc. to produce magnetic flux. Point to remember. You can understand the relationship between kW, kVA and kVA better by considering the following analogy. Suppose you went to a coffee shop and ordered for a cup of espresso coffee. You will find that a certain portion of the top of the cup is filled with foam which will not taste as real coffee, figure 1.2. This foam may be expressed as kVA. The portion below foam is the real coffee and may be represented as kW. The total quantity of the cup, i.e., the coffee, kW, and foam, kVA, is kVA. Now we are ready to define power factor. Figure 1.2, analogy of kW, kVA and kVA. Look at the screen. 1.4.6 power factor, PF. The power factor is the ratio of active power, kW, and apparent power, kVA, and is measured as cos phi, see figure 1.3. Thus, power factor, cos, equals active power, kW, upon apparent power, kVA, equals kW upon kW whole square plus qua whole square powers 1 upon 2. It may be seen that if kVA approaches 0, foam approaching 0, then kW and kVA would be almost equal, less foam, more espresso coffee. Thus, PF varies from 0 to 1. The power factor should be close to 1 so that only active power is involved. You will learn later in the course the possible ways to improve low power factor by installing capacitive loads. The power factor could be lagging or leading type. Lagging and leading power factors. Power factor can be lagging or leading type. When current lags the voltage, like in inductive loads, it is called lagging power factor. However, when current leads the voltage, like in capacitive loads, it is called leading power factor. 1.4.7 kWh, kWh. You must have come across the term, unit, while reading your monthly electric consumption bill. 1 unit of electricity, 1 kWh, is the energy consumed by 1000 watts bulb in 1 hour. Example 1.4. A three-phase induction motor, 25 kilowatts, is used for pumping water. The operating parameters are V equals 440 volts, I equals 25 amps, PF equals 0.95. Find energy consumption by motor in 1 hour. Solution. For a three-phase line, the power consumption is calculated by using EQ 1.5. Thus, energy consumption equals 1.732 into 440 volts into 25A into 0.95, PF, into 1 hour, 1000. Equals 18.1 kilowatt hours. Point to remember. Electricity as an energy carrier. Electricity is the most well-known energy carrier. Electricity is used to move the energy in fossil fuels and other energy sources from power plants to user end. We also use electricity to move the energy in flowing water from hydropower dams to consumers. For many energy needs, it is much easier to use electricity than the energy sources themselves. 1.5 Basics of thermal energy. Temperature and pressure are related to energy contained in a substance. Heat is a form of energy and temperature and is a measure of its thermal effects. Temperature is measured in degrees C in Celsius scale. You may recall the steam engines used in railways, where the heat energy was used to rotate the flywheel of these engines. We make use of heat energy daily in diverse areas. You get in your home's electricity which comes from thermal power stations. Pressure is an indicator of stored energy. The steam at high pressure contains more energy than that at low pressure. 1.5.1 Heat and specific heat. You know that heat is a form of energy. It is the energy of moving particles, atoms and molecules, of liquids, gas and solid matter. Calorie is its unit, but now, a day's joule is used as unit of heat. The specific heat is the quantity of heat required to raise the temperature of 1 kilogram of a substance through 1 degree Celsius. You can do a very simple experiment at your home. You take same amount of water and milk and supply same amount of heat to both of them. You will observe that their temperatures are increased by different amount. 1.5.2 Quantity of heat. The quantity of heat, Q, supplied to a substance having mass, m, and specific heat, Cp, is given as follows. Q equals mCp delta T. 1.9, where delta T is the increase in temperature. 1.6 Energy and thermodynamics. 1.6.1 Internal energy. Internal energy, as the name implies, is related to the internal structure of the substances. The translations, rotational and vibrational energies of the molecules are the example of this. All these energies can be influenced by the interaction of heat. 1.6.2 The laws of thermodynamics. We will confine ourselves only to the law of conservation of energy at moment. The energy of a system remains constant if the system is isolated from its surroundings. This also implies that energy can neither be created nor it can be destroyed. Point to remember. One of the important laws of physics is that energy is conserved. This means that energy will remain at the same level in a closed system. Our Earth is a closed system. 1.7 Various forms of energy. Energy use in India is increasing quite appreciably for commercial and industrial applications. The increase is almost 5% per year. The energy resources used are coal, biomass, wood and cow dung, oil, petrol, diesel and kerosene. Electricity. About 70% of electricity in India is generated by polluting coal. Energy exists in many forms. Broadly speaking, we can classify energy into two types, potential and kinetic energy as shown in figure 1.4. Look at the screen. Figure 1.4, Forms of energy. We will now define these forms of energy in the following sections. 1.7.1 Potential energy. The potential energy is the stored energy and the energy of position. Gravitational. Potential energy exists in many forms as discussed below. Chemical energy. The energy stored in the bonds of atoms and molecules is called chemical energy. The examples of stored chemical energy are petrol, diesel, kerosene, natural gas, coal, wood and other biomass. The stored chemical energy is released as heat when these fuels burn. How can you say that petrol actually burns inside a car engine? The petrol gets evaporated and gets mixed with air when it is sucked into the engine. This mixture gets exploded when ignited by an electric spark, i.e., by spark plug. The heat energy so released expands the gases inside the engine that moves the piston. Nuclear energy. The energy stored in the nucleus of an atom, the energy that holds the nucleus together, is called nuclear energy. The examples are nucleus of uranium atom. Modern societies are using nuclear energy in nuclear power stations to generate electricity, to power submarines and ships etc. Stored mechanical energy. The energy stored in the objects by the application of force is called stored mechanical energy. The examples of stored mechanical energy are compressed springs and stretched rubber. Gravitational energy. The energy by virtue of place or position is called gravitational energy. The water stored in a reservoir in a dam is the best example of gravitational energy. This energy can be released when the flow of the river is controlled to produce electricity at a dam. 1.7.2 Kinetic energy. The energy of motion like the motion of waves, electrons, atoms etc. is called the kinetic energy. The kinetic energy also exists in many forms, the most important being the radiant energy. Radiant energy. The radiant energy is electromagnetic energy. You are familiar with X-rays, visible light, radio waves, gamma rays etc. All these are radiant energy. Solar energy, which we will discuss in detail in this course, is also an example of radiant energy. How can you say that light is energy? Can you visualize that light may cause things to move? Your answer should be yes. Take a solar cell and connect it to a galvanometer. When sunlight falls on the cell, the needle of the galvanometer moves. The moment you shade the cell by your hand, the needle comes back to its original state. Thus, the light causes things to move. 1.7.3 Thermal energy. The internal energy of substances is called thermal energy. Geothermal energy is an example of thermal energy. Motion. The movement of substances from one place to another is energy associated with motion. The examples are wind energy and hydropower. Sound. The movement of energy through substances in longitudinal waves is called sound waves. Electrical. Electrical energy is the movement of electrons. The example includes electricity and lighting. You should remember, energy is all around us. Energy exists in many forms. Energy can be detected by our senses. Energy is stored in different situations. Energy can change form and can be used to do useful work. All changes in the universe involves the interaction between energy and matter. 1.8 Units of energy. One of the units of energy measurement is the BTU, or the British Thermal Unit. 1 BTU is the amount of heat energy needed to raise the temperature of 1 pound of liquid water by 1 degree Fahrenheit. If you apply a voltage, a form of force, of 1 volt to a resistance of 1 ohm, a current of 1 ampere results and the resistance dissipates a heat power of 1 watt, W. 1 horsepower is equal to 746 W. 1000 watts is a kilowatt, and 1,000,000 watts is a megawatt. 1 watt of power present for 1 second represents an energy quantity of 1 watt second, and is called a joule, J. We also have larger kilojoules, megajoules, and gigajoules. One of the most preferred units of energy is watt. R, Wh, its larger kilowatt hour, kWh, and megawatt hour, MWh. 1 joule is 1 watt second, and there are 3600 joules in 1 watt hour. Watt hours are easily understood. A point to remember. A kilowatt hour is consumed by burning a 100 watt light bulb for 10 hours. 100 W, 10H equals 1000 watt hours equals 1 kilowatt hour. A microwave oven draws about 1 kilowatt hour in 1 hour of operation, or about a week's normal use. A solar-powered calculator consumes about 1 watt hour of energy over its actual use. Lifetime. Running upstairs, as fast as a fit person normally does use about 200 W or just under quarter horsepower. Doing so continuously for 5 hours requires a kWh of energy. There are 3412 BTUs in a kWh. You know that energy is defined as the capacity to do work. The SI unit for energy is the same as the unit of work, i.e. the joule, J. 1 joule is equal to 1 Newton meter. In CGS units, 1 ERG is equal to 1.0 times 10⁻⁷ J. The energy unit used for everyday electricity, particularly for utility bills, is the kilowatt hour, kWh, and 1 kilowatt hour is equivalent to 3.6 times 106 J, 3600 kilojoules or 3.6 megajoules. Electricity usage is often given in units of kilowatt hours per year. Kilowatt hour per year. This is actually a measurement of power consumption, i.e., the rate at which energy is transferred. The calorie equals to the amount of thermal energy necessary to raise the temperature of 1 gram of water by 1 Celsius degree, at a pressure of 1 atmosphere. For thermochemistry, a calorie of 4.184 J is used. You are familiar with widely used source of energy, i.e., coal or oil. In order to give you an idea how much energy is contained in 1 ton of coal or oil, we have to use a bigger unit, i.e. gigajoule, GJ. 1 giga equals 10 powers 9. 1 ton of coal equivalent, TCE, equals 29 gigajoules. 1 ton of oil equivalent, TO, equals 41.87 gigajoules. The energy conversion factors are listed in Table 1.8.1. Table 1.2. Energy conversion factors. Look at the screen. 1.9 Let US sum UP. Energy is the ultimate thing in the universe. Energy is the capacity to do work. Energy is the ability to employ a force that moves something through a distance. Energy performs some exact electrical, thermal, chemical, or whatever equivalent to mechanical work. Power is the time rate of doing work. Thus, energy is how much and power is how fast. One older unit of energy measurement is the BTU, or the British thermal unit. This is the amount of heat energy needed to raise the temperature of 1 pound of liquid water by 1 degree Fahrenheit. Energy exists in many forms: heat, light, electrical, mechanical, chemical, kinetic, potential, solar, etc. Energy is always conserved. It can neither be created nor be destroyed. Energy can change one form to another. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.